Good morning, students. In last lecture we have discussed about work. So what is work? Okay, yes, chapter 6, work, energy, power. In last lecture we have discussed about what is work done by a constant force. Okay, if during the process or during motion of an object, force acting on object is constant, then what is work? Work is equal to component of force in direction of displacement into displacement. Okay, that is W is equal to F dot D, FD cos theta, where theta is angle between force and displacement. But what is work done by a variable force? Variable force means when object is in motion from one point to another point, initial position to another position, and during this motion, if at each and every point force is not uniform, so yes, when force is not constant, it is said to be variable force. So what is work done by a variable force? What is work done by a variable force? That we will understand with the help of one illustration. See, what is work done by variable force? Suppose one object is moving from point A to B. Suppose one object is moving from point A to B. A initial position, B final position, under the influence of a variable force. Variable force means at this point force different, at this point force different, at this point force difference, at each and every point, force is different, means force is varying, okay, yes, force is varying. So here let object is moving from point A to B, under the influence of variable force, okay, yes, force is varying from initial position to final position. So during such motion, how to calculate work done? See, we can divide this whole part in very small elements. So first is divide part AB in small elements. Small elements means I can say small displacements, that is small displacement. Clear about this? So yes, I can say it like this. I can divide this whole part in very small displacements like this. Okay, I can divide this part in very small displacement. Okay, take one element. Okay, let it is one element. Now see, as we divide the part AB in small elements, that is small displacement. Okay, if this displacement is small, we can consider okay, during this small displacement, force is constant. Yes. On the whole path, force is not constant. At each and every point, its value is different. But if I am taking elements small, for an element for very small displacement, I can consider that force to be constant. So yes, here take one element very small. Okay, so yes, for that element, for such small element, we can consider force to be constant. Clear about this? We can consider force to be constant. So just I am assuming that force acting on this element is F, and this displacement is, let it is here, and this displacement is, let it is here. Clear about this? So yes, take one element very small. For such small element, we can consider force to be constant, and due to force, let displacement is here. Clear about this? Take this one element. We are assuming over such small element force is constant, and due to that force, let displacement is here. So what is work done? What is work done for small displacement? dr. What is work done for small displacement dr? Delta W is equal to, delta W is equal to, yes, delta W is equal to, it is F dot dr. Delta W is equal to, it is F dot dr. Clear about this? Clear about this? Yes or no? Now what I have to do, see, it is only work to bring from this particle from this point to this point, means this must displacement. Okay. Delta W is work done for displacement dr. If I want to move this object from A to B, yes, initially it is displaced by displacement r, another displacement dr, another displacement dr, another displacement dr. So what I have to do? First of all, find work done for this displacement, 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 and to find total work done from A to B, you have to add such all work done. Clear about this? Okay, so to find total work done, to bring object from A to B, work W is equal to, it is sigma of delta W. Means work done for this displacement plus work done for this displacement plus work done for this displacement plus work done for this displacement. So yes, total work done to bring object from A to B, W is equal to sigma delta W. Clear? Now as here displacement dr tends to 0, means very small, so yes, we can say that this sigma, that is addition, converts in integration. So yes, as here displacement dr tends to 0, we can say WAB is equal to integration of delta W from A to B. And what is value of delta W is F dot dr. So WAB is equal to integration A to B F dot dr. It is WAB is equal to integration A to B F dot dr. WAB is equal to integration A to B F dot dr. Clear about this? Okay, so yes, it is equation of work done for a variable force. Clear about this? Yes. In future, okay, some of the most important theory we will prove from this equation. Okay, in 12th chapter number 2, electrostatic potential energy, we will start theory from this equation. Okay, so yes, it is one important equation. WA is equal to A to B F dot dr, where F is force and dr is displacement. Dr is displacement. Clear about this? Clear about this? Okay, so yes, it is work done by a variable force. Now, we will take one special case. If object is moving in one dimension, if object is moving in one dimension, okay, object is performing one dimensional motion, object is performing one dimensional motion, then how to modify this equation? Okay, let object is performing one dimensional motion, okay, that is only in x direction, yes or no, and force is also in direction of displacement, okay. So yes, when force and displacement, they are in same direction, we can say angle between them is 0. Then how to reduce this equation? See, W AB is equal to integration A to B F dot dr is equal to, it is F dr cos 0. It is F dr cos 0. Cos 0, it will be 1. So yes, here it is WAB is equal to, here it is from integration A to B F dr. It is F dr. And as object is moving in one dimension, we can also write this equation in terms of x. We can also convert, or we can also write this equation in terms of x. For example, if let it is one graph, it is x, it is force. Object is moving in one dimension from x1 to x2, under the effect of variable force. It is moving from x1 to x2. Then how to modify this equation? See how to modify this equation. Here W is equal to integration x1 to x2. It is moving from x1 to x2. Integration x1 to x2, and here it will be f dx, and here it will be f dx. So yes, for motion in one dimension, that is on x-axis, I can write equation of W is equal to x1 to x2 f dx. W is equal to x1 to x2 f dx. Clear about this? Motion in one dimension, and when they both are in the same direction, then W is equal to, it is x1 to x2 f dx. Clear about this? Okay, but the general equation of work is W is equal to A to B F dot dr. Okay, now see here. We will understand this concept with the help of this figure. Okay, yes, object is moving from this x1 to x2 under the effect of variable force for very small displacement, that is from this point to this point. Okay, this point to this point. We have to find what is work. So yes, if this graph encloses some area with fx graph, for another displacement, it is graph enclosed by fx graph. For another displacement, it is graph enclosed by fx graph. For another displacement, it is graph enclosed by displacement. Okay, so yes, if it is graph from x1 to x2, then yes, it is area enclosed by fx graph. It is area enclosed by fx graph. And yes, see definition here. W is equal to f dx. So yes, it is value of f and it is value of dx. So yes, this f dx is area of this rectangle. F dx is area of this rectangle. Yes or no? Yes, it is. This f dx is area of this rectangle. What is integration x1 to x2 f dx? Between x1 and x2. Between x1 and x2. Addition of such all area. Addition of such all area. Addition of such all area. It is called work done. It is called work done. So yes, area enclosed by fx graph, it gives area enclosed by fx graph, it gives work done. It gives work done. Clear about this? So yes, this point, this last point you have to remember. This last point you have to remember. Okay? Okay, when you are given f versus x graph, when you are given f versus x graph, the area enclosed by fx graph, the area enclosed by fx graph gives work done. Gives work done. Clear about this? So yes, today's topic is work done by a variable force. Now next topic is kinetic energy, and yes, what is work energy theorem? Yes, it is one of the important topic, and yes, it is one important theory. Okay, what is kinetic energy and what is work energy theorem? What is work energy theorem? See, we will understand this with the help of one example. See, for example, if it is one surface, one block is there, one block is there, having mass m. Its initial speed is 0. Its initial speed is 0. If we know that Newton's first law of motion, if we apply some external force, there is change in its velocity. Okay, means it is performing accelerated motion. So let some force is applied, and due to that force, its velocity changes to v. Yes or no? Yes or no? Some force is applied, and due to that force there is change in velocity. And yes, during this displacement is v. That displacement is v. Okay? Yes. So initial velocity of object is v0, final velocity is v, and displacement is v. So yes, what is relation between v0, v, and v? Okay? And yes, force is applied. Force is applied. So due to force, acceleration is produced. So what is relation between these all quantities? What is relation between these all quantities? See, let initial velocity is v0. Force F is applied. Force F is applied. Okay, so change velocity, so final velocity is v. Final velocity is v. Okay, and what is displacement during this journey? Displacement due to force. Displacement due to force is v. So what is relation between these quantities? Yes, we know this. We know one equation, that is v square minus v0 square is equal to 2AD. V square minus v0 square is equal to, it is 2AD. Clear about this? Yes, v square minus v0 square is equal to, it is 2AD. Initial velocity, final velocity, acceleration produced due to force is A, and displacement is T. Now I will multiply this equation by m by 2. Okay, multiply equation by m by 2. So yes, if you multiply this equation by m by 2, what happens? See, here it is m by 2 v square minus m by 2 v0 square is equal to, it is 2AD m by 2. So this 2 cut, this 2 cut. Yes or no? So yes, here I can write this equation as half m v square minus half m v0 square is equal to, yes, I can write this equation as m a. Here it is v. Here it is v. See, what is mass of clock? It is m. Okay, force applied is F and due to that acceleration produced is A. So yes, according to Newton's second law of motion, I can write m is equal to force. So yes, it is half mv square minus half mv0 square is equal to Fd. Clear about this? Yes, the system is in one dimension. This system is in one dimensional motion. Yes or no? It is moving in one direction. Okay, so yes, half mv square minus half mv0 square is equal to Fd. Due to this force, it is displacement. Due to this force, it is displacement. So yes, this Fd is nothing but work. This Fd is nothing but work. Half mv square minus half mv0 square is equal to it is work. Okay, yes, we know that this W is work. Now see, left hand side, it is half mv square, half, that is half m mass, v that is square of speed, minus half mass again, v0 that is again square of speed. It is square of final speed and it is square of initial speed. Now you have to remember one point, that whenever you are given such equation, okay, then the dimensions of each and every term remains same, or it is same. Dimensions of each and every term is same. How? See, we have proved one equation, that is C. Here it is. We know that this equation, it is x is equal to v0t plus half at square. Yes or no? Chalo, what is unit of x? Meter. What is unit of v0t? Meter. How? What is v0 initial speed? Unit of speed is meter per second and t is second, so second. So what is unit of v0t? It is obviously meter. Clear about this? Half at square. Half, that is, yes, it is number, so no unit. A acceleration, its unit is meter per second square. T square, its unit is second square, so it is. Yes or no? So yes, whenever you are given one equation like this, okay, dimensions of each and every term, they are same. X, its unit is meter. V0t, its unit is meter. Half at square, its unit is meter. Yes or no? Yes or no? Yes, it is. So here W is equal to half mv square minus half mv0 square. It is work. Or yes, we can say it is one form of energy. Then yes, this half mv square and half mv0 square. It is also one form of energy. Here, half mass into speed square has dimensions of energy, because work and energy, they having same dimension, Here half mass into speed square has dimensions of energy, okay, and as it is half mass, v that is speed, and speed is due to its motion. Whenever object is in motion, it has some speed. So yes, this term, that is half mv square. Okay, that is half mv square. Okay, here half into mass into speed square is called kinetic energy. Half mv square, v that is final speed. So yes, what is half mv square and what is half mv0 square? See, we will see. Here it is half mv square. It is called half mv square. It is called final kinetic energy. And half mv0 square, it is called initial kinetic energy. There about this. So yes, this half atmosphere final kinetic energy I can write as Kf, and here I can write as Ki. Okay, so how to write this equation now? Half mv square I can write as Kf minus half mv0 square I can write as Ki. So Kf minus Ki is equal to, it is W. And Kf minus Ki, final kinetic energy minus initial kinetic energy, it is called delta K, is equal to W. Is equal to W. Clear about this? So yes, what is this equation? Change in kinetic energy is equal to work done. Change in kinetic energy is equal to work done. Change in kinetic energy. Change in kinetic energy is equal to work. Is equal to work. And it is called work energy theorem. And it is called work energy theorem. W is equal to delta K. W is equal to delta K. It is called work energy theorem. Clear about this? Yes, one topic, that is what is kinetic energy. What is kinetic energy? If we have an object of mass m moving with speed v, then energy by virtue of its motion, energy by virtue of its motion is called kinetic energy. Is called kinetic energy. Ability to do work, it is energy. Ability to do work, it is called energy. Now ability to do work by virtue of its motion is called kinetic energy. Okay, ability to do work by virtue of its motion, by virtue of its motion is called kinetic energy. Is called kinetic energy. Clear it is? Okay, and what is equation of this kinetic energy? Yes, if we have an object of mass m moving with speed v, then its kinetic energy K is equal to half mv square. It is half mv square. And as kinetic energy is nothing but ability to do work, means dimensions, unit of work and energy we are saying. Kinetic energy is scalar quantity. Kinetic energy is scalar quantity. We know that mass is scalar. So yes, here this V is also scalar. Or we can say this V is speed, not velocity. This V is speed, not velocity. This V is speed. This V is speed. Okay. So K is equal to, it is half mv square. K is equal to, it is half mv square. Clear about this? We can also write one equation of kinetic energy. We know that, see, if I multiply this equation, it is half mv square. I am multiplying by m and dividing by m. Okay, then say numerically it becomes m square v square. We know that momentum P is equal to mv. Momentum P is equal to mv. So m square v square, it will become p square. So it is p square upon 12. So it is another equation of kinetic energy. A kinetic energy K is equal to p square upon 2m. Kinetic energy K is equal to, it is p square upon 2m. Where p is linear momentum. 2, that is 2, and m is mass. Clear about this? So yes, what is kinetic energy and what is work energy theorem? Changing kinetic energy is equal to work, that is work energy theorem. And yes, this theorem is important to prove some theory in future, that is in another chapters in 12, and most important use is in 12. Okay, so yes, take care about these topics.